Everyone, Anthony here, and you may notice I'm grinning and looking a bit silly. It's because this was actually meant to be a two-part, a longer video, and it turns out the thing we're building here, which I need to demonstrate another concept, just took too long to do, so I decided to break it into its own thing. So we're going to do something really silly and stupid, and we're going to build the curve tool, or we're going to build a bit of the curve tool. I laugh because you wouldn't do this, but you kind of might. Anyway, let's see what we get. This is going to be fun because it's just silly. We haven't done something silly for a while. So let's put down the curve tool here and plug it into our setup. Now our setup is just 3 noise nodes here that's on red, green, and blue, and they're just animated. Reason for that is we want to use the curve tool, reset the region of interest, never remember to do that, and we want to get the max luminance data for each pixel. So we'll just calculate it for 1001 to 1010, so standard 10 frames. Right, we end up with a max luma data, which is a pixel that floats across the screen. We have particular locations for it and what the value is. So we can actually use this as a reference and make sure our code works. Right, so that's our reference here. Close that now. Now, to do this, we're going to be using the sample function. We'll put down a NoOp, of all things, NoOp. Funnily enough, this actually comes from Houdini, or at least Houdini practice, I believe. So they'll call it a null, but I've got a NoOp here, handy dandy NoOp. NoOp doesn't do anything, so I'm just going to rename it to sample me, so all in capitals. Now, the reason for it is we now have this handy thing that we can just say, we're going to sample the node graph at this point, right? So every node in Nuke has a sample function on it. There is this Nuke sample that you can use. Please don't use it. If you see the help, you'll actually see it says sample ncxdydx float. Sure, right. N is the node you want to sample at, but it actually does say this one, deprecated. Deprecated for a developer is code for please, please, please stop using this. We want to get rid of it, but we can't because someone screamed last time we did it. Help out your developers. Don't use deprecated functions if you can. There's a better one. It actually says use node sample instead. So we're about to do that. Deprecation is one of the great challenges of code. Once you put something in place, people use it, and once people use it, it's very hard to get them to stop using it. So we're going to go to the node sample me, right? We're just going to grab the node here. And we're going to do on the node, we're going to use the same call, sample. We don't have to pass the node in because it knows to sample at this point. So we're going to sample using the format of RGBA.red. So we're going to sample the red channel, and we're going to pick a pixel location 00, which is the bottom left-hand corner of the screen here. All right, this guy. So this is the value of the red channel, 0.138 something, which is that number here. Now, the reason for doing it this way instead of going to noise 3 is because we're using this as just a way to probe the image. So if I put down a checkerboard, plug sample me in here, we should expect this value to be this 0.1 gray value. Right, and you can see it is 0.1. That stuff here is just because of floating point precision, which I think I've mentioned before, but yeah, floating point numbers aren't, they're handy, but there's precision issues. So yeah, that's why I have this NoOp. So I can just plug it into wherever I want and know that my code doesn't have to change. I just say, go to the node called sample me and sample the image from this point. It's like how you have a viewer, you just put the viewer in various places. So your viewer's looking at the area you want to look at, right? So in some ways, we're using our sample function as kind of like a viewer, and this is our pseudo viewer. So it's now going to look at the curve tool. It's going to look at the checkerboard, look at the noise node up here without the blue on it, or look at everything. So that's sort of just why I do it like this. Now, slight note as well. Let's put the viewer on so we can see it. The pixel location of 00, there are some considerations here. Now, let's I'll just plot the help for this. So it actually does have, let's get some more space. That's really long. So it tells you, where are we? Oh God, here we are. So this requires the image to be calculated, so it can be very bad, so don't do it. It's an expensive call because how do you know what color the pixel is unless you render the image into a viewer, basically. But here it says, produces a cubic filter result. Any sizes less than 1, including 0, produces an area. Note that integers are the corner of pixels. To center on a pixel, add 0.5 to both coordinates. So, first thing, here in this image, we can only select full discrete pixels. So this is, let's say, 0, 0. I actually don't know what pixel. I wonder if that's 0 or 1. Let's find out. So x is, let's do 0, 0. 0.13835, which is clearly this pixel here. It's not this one. It's not this. No, it's not this one. It's this one. If we do 1, 1, 1, 1286, which is, yeah, okay. So they're referring to this pixel here as 0, 0. And had I been smarter, I would have actually remembered. I can actually see that here. Let's shrink that across. So you can see x is 0, 0. 1, 1, 2, 1. So this is what it refers to the pixel as. But it says that the integers are the corner of pixels, so it is literally this tiny corner here. So 1, 1 refers to this corner right here. Now, if we're asking for a region of 1 pixel only, so 1 by 1, it doesn't matter, and it tells you here. If the optional dx and dy, so delta x, delta y is what that stands for, so the difference in x, difference in y, that's a good enough way to remember it, are not given, then the exact value of the square pixel that xy lands in is returned. So 1, 1, oops, 1, 1 gives you this pixel here. 0, 0 gives you this pixel here, so that's fine. But you can actually use dx and dy to give you a larger region. So this, a sample region, and this is a sample region. So let's just do that. So here, if we were to do this as a sample region, the center is, I actually don't know what the center would be. Let's do a 3 by 3. It's easier. So if we sampled this 3 by 3 region, the channel is red, the center, I actually haven't done this live, so let's find out. So the center of the area to sample would be, naively, let's say we took this pixel as a center, it'd be 1, 1. So 1, 1 is the correct pixel. And we want a width of, I think we want a width of 3 by 3? 1 point, yeah, I think that's it. So, okay. Let's do this separately. And then 1.5 and 1.5. Nope. 1.4. I'm trying to get this number here, 0.14346. What is the width on that? 1.5? No. Thought process here is I don't actually. No. 2? I'm just trying numbers while I'm just theorizing what that dx dy could mean. Oh, it's going to be 3 by 3. It is. Yeah, it is 3 by 3, that's correct. 1417. I'm just not sure how it's getting 0.14346 for that region. 14346. Okay, weird. As you can see, I don't use this all that often, to be honest, not to do this kind of thing. Or if I do, I just care about broad brush strokes. So that's why I don't know. I'll leave this in the video just as proof that sometimes you just muck around and you just go, I don't actually understand. You sort of have to go and figure this stuff out. It's going to bug me. Note that integers are the corners of pixels. To center on a pixel, so we want to center on this pixel here. This pixel is considered pixel 1, 1. Add 0.5 to both coordinates. So that is really 1.5, 1.5. dx. Optional size of area to sample in x coordinates and y coordinates. 3. I don't know why that doesn't work. Huh, weird. Okay, we'll ignore that for now. Let's just pretend I never made that mistake. It's not important for this demonstration because we just really care about the x, y value of a pixel, which we know is easily picked out. So let's just do this, x is 0, y is 0. So we just set this up with a parameter here, and we can just print that out. Cool, so it's 1383.5, which is this value here. Comfortable with that one. So let's just expand this out to red, green, and blue. So red is that one, green is that one, and blue is that. So we should be able to pick the red, green, and blue values of this pixel now. And importantly, going back to our original brief type thing, we're going for luminance. Now, luminance is a specific concept. So let me bring up Wikipedia. So relative luminance is where I'm at. And it's relative. You can read this through. I won't go through it. But basically, this is the formula we're after. This bit. Relative luminance can be calculated from linear RGB components, which we're in linear space and everything. First, convert the gamma blah, 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 blah to linear RGB. We've done that. And then do this. Y equals decent amount of red, a stack load of green, and almost no blue. So I'll just move that aside. We'll type that in now. So that is luminance equals 0.2126 times your red plus 0.7152 times your green plus 0.0722 of your blue. Right. If you played much with the colors, you probably feel this actually makes sense. Your green areas are going to feel hotter. Like that's the even if I look at this image now, I mean the pink seems pretty kind of crazy, but I think the pink is, I don't know why. It could just be me. But if we sample this and change this into luminance, you'll see the color. Let's just redo that. So it's ins, linear, out is HSL. Hue, saturation, luminance. Nope. Hue here. Hue, saturation, luminance. All right, so luminance here. This should map kind of closely to the green values primarily. Like, I think that's the green. No, it's hard to do stuff when you're just guessing. We'll go back to that in a second. Anyway, so I can now calculate the luminance for a certain pixel, and we can drive it off this set of variables here. So now let's decide to sample the image, and let's work in Nuke sense. So let's go left to right and bottom to top. So scan line by scan line, effectively. I mean, we could go top to bottom, but because the bottom left-hand corner is 0, 0, makes life a lot easier. We just start from 0 and keep going up. So what we need to do is we need to work out, first of all, how wide this image is, and then how tall it is. I know it's squared 256, we know the answer, but the node dot width, and let's do height. Right, so the width is 256 and the height is 256. No guesses there. So going into what we said we wanted to do, we wanted to go left to right first. So let's start with our inside loop. Right, so for the x coordinate, which is in the range from bottom left hand corner or leftmost, which is 0, and then the rightmost, which is the width, right? Then we want to do this. So this will immediately give us the red, green, and blue and the calculated luminance going left to right. Now the next thing we want to do is we want to go up in terms of scan lines. So we take that function, indent it one more level, and go like this. For y in range from 0 to the height. And because we parameterize it to use x and y, they just sort of flow through here. So that should basically walk us left to right, and then when it's finished, go back to the start, walk us left to right, and go up the image. This is, by the way, not very efficient, but you know, it illustrates the idea. You'll see how not efficient it is in a moment, actually. So the next thing we've got is, we've gone through every pixel, we'll go through every single pixel in the image, and then we'll be able to calculate red, green, blue. We'll be able to sample red, green, and blue, and then we'll be able to get the luminance out. So now let's just find the maximum luminance. All right, so max lum equals, we assume it starts at a value of 0. And where is it? We'll assume it is at the coordinate 0, 0. Fine, it's a decent assumption to begin with. So now we've calculated the luminance for whatever pixel we're at. If the luminance is greater than the old max lum, then obviously we found a new brightest pixel. So max maximum equals luminance. So we update what our maximum was, and we just update where it was, where equals x, y, so the new coordinates. So let's just run that all up. Cool, it's done, relatively quick. So let's print where? That's the pixel location where we found the max luminance. So let's then extend this to just run across our frame range. So start equals 1001, end equals 1010. For frame in range from the start to the end, take all this stuff, indent and cross, and we should be okay, except for I've forgotten one thing. We need to reset it on each frame. So if I didn't have that there, let's put that nearer to the top. If I didn't have this here, I'd be going maximum luminance pixel at a location across all frames. Not quite what I want it per frame. So obviously when a frame starts, it resets itself to 0. It assumes the brightest pixel's bottom left-hand corner, and it's not bright at all. Does the calculation and continues. So let's see what we get. And I have made a mistake. I forgot to I'm running this code 10 times. I'm not actually updating the frame. Yeah. Oops, I forgot to do that. So the sample function, it's something that I wish they'd fix in the help, which they probably won't fix in the help unless I mention it, but yeah. Here, this just seems to imply, if you didn't read the rest of it, this seems to imply you can only get C for channel, X for X, Y for Y, D, X, dy, so size. But if you go down here, there's a parameter called frame, an optional frame to sample the node at, which is what I'm feeding in here. So yeah, let's do that again properly. Yeah, all right, so we got some results, and let's just cross-check against the curve tool. So on frame, what the? Why is the? Oh my God, why does no one tell me this? I've just sampled red 3 times. Gah. That's why it's useful, by the way, to have reference and test cases. So you just go, that doesn't look right. Let's try that again. Okay, this is a bit better. So 248.16, 92.05, 82.173. Now there is a discrepancy here. 92.05, that's the same. 82.173, that's different. 129.19. 91.113. They're close, but they're out. I wonder. Okay, so there's many possible reasons for this. One possible reason, you could be looking at this and going, maybe these constants aren't precise enough. I have pulled them off the Wikipedia page, but I'm pretty sure those are the correct constants, because otherwise you would have more info there. Like, it's very unlikely that these values are going to be much more precise than that, because it's a pain for everybody. Yeah, like if you're going to define this, you're going to define it to a certain level of precision, say that is the calculation. All right. What's more likely to be stuffing us up is, remember we went through that plus 0.5 thing? Let's just try the voodoo magic. I actually don't know if this will work, but I have a feeling it might. Let's try that again now. Yeah, that's actually spot on now. Interesting. So while the documentation states if your region is a size of 1, it doesn't matter, it'll get you the pixel. I actually think that there is some sampling going on here. The numbers we see here, which I'm using to reference off and cross-check my work, they're not sufficiently detailed, so I actually do have to sample it. I mean, what could you do? You could actually not sure how you check it outside of this code. You crack it open in OpenImage.io or something. But anyway, yeah, looking at those numbers now, so we have 248.15, spot on. 90.205, spot on. 79.171, spot on. 129.198, spot on. 91.113, 5.117, 72.85, 202.113, 223.124. So yeah, that's interesting. I'll leave that in. I'm not sure what's going on there, but play with it and do some cross-referencing. But yeah, that is a bit more of a dive into the curve tool, this bit of it, but more accurately, it's a dive into how you would build this way using the sample. And I mentioned it's slow, so how can I demonstrate? All right, so we're doing the same 10 frames. We're going to do it again, but I'll just keep talking. I press the enter now, and I still have more words before anything comes up, and oh god, yep, it's done. So it took that long. I'll time it and I'll put a timestamp up there. The curve tool, on the other hand, let's just do go, and it's done. It's a lot faster. There's reasons it's a lot faster. It's probably clever enough to read the whole image at one. Actually, no. It's probably better threaded, and also this is probably done in C. This is done obviously in some sort of Python's got to go request information from Nuke, which is going to give it back to me, which I'm then doing all my loopy stuff here. There's probably much more efficient ways to do it. My gut feeling would be that let me try something. Okay, yeah, I can do this. All right, so let's bring up the resource monitor on my computer. Cool, there we are. Let's make it a bit tall. Well, that'll do. All right, let's also just basically, I'm working off a theory that my Python code is basically single-threaded and slow as a dog, and the curve tool is a lot faster. So this speed is too slow. So bring up. Let's change the full size format to something. No, let's go insane. Sure, that works. This is going to be painful. So using the curve tool with max luma pixel, let us reset the region of interest, go and do it for 10 frames. Let's watch the graphs. Yeah, okay. So you'll see a whole bunch of spikes, everything's going maxing out. So that's good. That's what we're seeing. That's what we're seeing here. Like you can see this maxing point. These other threads is because OBS is recording right now. Right. So we've got that all quiet. Now let's do our code. And because we wrote everything using sample me node and I can recalculate the width and the height, totally fine. Let's see what this looks like. And I've hit enter and let's have a look. So you see this spinning wheel of doom. So something's happening, but nothing very fast is happening. Oh God, what have I done? Maybe I shouldn't have chosen this image size. Yeah, okay, cool. So that probably does prove the difference here. You can actually see there looks like there's one of my cores that has been loaded a bit more heavily, which is this guy down here, and this one possibly. But most of my computer is just like chilling, really just chilling here. So that probably explains the speed difference between the curve tool and the Packy Python version I've got. If you were to do this using OpenImageIO, I'm pretty sure it would suck down every single thread it can get its hands on. But yeah, so yeah, I'm gonna pause this one here and then we'll come back to it. But this hopefully was just a bit of fun to take apart and build this thing. Now, as a preview of the next thing, I'm actually going to use this, maybe not this specific size of rig. I might go to 512 square rather than 256 to demonstrate the best practice, or at least my version of best practice when putting up a progress indicator. Because right now, as you can see on the screen, this is really frustrating for an artist. Like, this is what you get. I think it, like, you know, what can you do here? Your artist is just sitting around. They can't tell if you've crashed the computer or if something's processing, or even having a cancel button. Alright, so because there's no real cancel button or way to interrupt this, then you end up with a situation where artists is like, alright, it's killing Nuke, and you may interrupt a relatively expensive process. So user feedback through a progress indicator is actually kind of important, which is what this rig was built to actually give us a chance to play with. So yeah, see you in the next one and we'll see how we go with that. Right, see you guys.